Now we're going to look at the function the cube root of x and determine where it's concave up and concave down and find any inflection points. So looking at this, before I even take the second derivative of it, I need to rewrite this function as f of x is really just the same thing as x to the power 1 over root 3. So we have x to the 1/3, and we're going to take the second derivative and set it equal to 0. So our first derivative, from bringing down the power, we're going to get 1/3 x to the 1/3 minus 1. So we're going to do some side work here again. 1/3 minus 1 is 1 minus 3 is negative 2/3. And now we're ready to take our second derivative. We're going to bring down the power. So we're going to do 1/3 times the negative 2/3 x to the negative 2/3 minus 1. So negative 2 minus 3 is going to give us negative 5/3. And you can use your calculator to do all of this, subtracting 1 from a fraction and even this multiplying of fractions. But I'm just doing it without a calculator. So I'm going to multiply these together. My second derivative is really going to be, the top is 1 times negative 2, which is negative 2. And in the bottom, 3 times 3 is 9. And we have x to the negative 5/3. And we want to set that equal to 0. So we want to think about solving something with a negative exponent. How we solve that is to put that negative exponent where it belongs. So I'm going to put that down in the denominator. It's going to be negative 2 over 9x to the positive 5/3. And then when we're solving a fraction, we just want to think about what makes the top 0 and what makes the bottom 0. So I'd want to think about what makes negative 2 equal 0. Well, negative 2 is always negative 2. I can't make that 0, so that's not going to equal 0. And then in the bottom, I have 9 times something has to equal 0. Well, the only thing that you can multiply 9 by and get 0 is 0. That makes f double prime undefined. It makes us divide by 0, right? So there's my special number, which in second derivative world is called an inflection point. Right now, this is a possible inflection point. It is not necessarily an inflection point until we figure out whether it changes concavity there as well. So we're going to call this a possible inflection point, and we're going to see on our sign chart whether it is an actual inflection point. If there's a change in concavity, we can call it an inflection point. If there's no change in concavity, then we no longer even going to consider it as an inflection point. So I'm going to put 0 on here first. This makes the second derivative undefined. So we do have the question of, can it go into the original and have a y value of a point, but we'll get there in a second. We'll just figure out what's happening with the concavity first. So if we plug in a number to the left of 0, maybe negative 1, I'm plugging into the sign of the second derivative. So the top of the second derivative is always negative 2. So the numerator is negative no matter what. In the bottom, I have a positive 9, so that's positive. And then I really just need to figure out, what is negative 1 to the 5/3? Is that positive or is that negative? So I'm going to grab my calculator. Negative 1 to the 5/3 is going to be negative. So in the top I have a negative, and in the bottom I have a positive times a negative, which is a negative. So I'll get a negative divided by a negative. This first interval is positive. Remember, we're not in increasing and decreasing world. Second derivative, we would call this concave up. So it might look something like part of a right side up U. After 0, I can plug in anything I want to. I'm going to plug in positive 1. The numerator is always negative 2, so the numerator is negative. In the bottom, 9 is always positive, so I'm going to have a positive there. And the question is, what is 1 to the 5/3? Well, 1 to any power is always 1. So it's going to stay positive. So I have a negative divided by a positive. This interval is going to be negative. So I'm going to switch and flip and be downward. So that would indicate I have an inflection point here. It's that part that looks like it's between the two concavities. Not right in the middle of concave up or in the middle of concave down. It's where it's switching between the two. There is our point of inflection. The question here is, though, is it actually even a point on the graph? Because it did make the second derivative undefined and not 0. I am concerned, can I plug it into the original function? So let's see if that works. So I need to plug it in. 0 into the original function, see if it doesn't give me an error. If it doesn't, then I'm good to go. So I'm going to do the cube root of 0, or if it's easier for you, you can do 0 to the 1/3. And does that work? Yes, you get 0 out. So we do have an inflection point because it does make the second derivative undefined, and it does have a change in concavity, and we also know it is a point on the graph. It doesn't give us an error. Even though it made the second derivative undefined, it didn't make the original function undefined. So we have a point of inflection at 0, 0, and then I just need to draw my conclusions about concavity. Remember, we don't switch at our random test values, we switch at our inflection point only. So when I write my interval of concave up, that's where it's positive, so it's the first interval, and that's going to be -infinity to 0, not -1. I made up that random test value. And then concave down is going to be from 0, our inflection point, onto infinity.